I will now hand over to you. Over to you.
Hand over to me, yes. So I just press the got it on here. It's come up. Yeah, okay. Well, thank you for the introduction, Vicky, and for selling my book for me. Very good. I hope it's been well used. Everywhere I go, offshore and onshore, I do notice copies around, so it's obviously proving useful. The talk tonight is based around lessons I've learned from all of you while I've been out running logging courses and training courses, especially on the chalk. And this picture is just an introduction to the main theme of the talk tonight, which is basically fracturing and marker beds. And on the screen, you will see you've got various marker beds. Some of them are named, things like the Marl seams here. And then you've got flint bands, which are also named. And then you've got styles of fracturing. In this case, you've got big steeply inclined fractures, conjugate fractures, which have been rotated from their original position in this fold. And this fold was probably completed in the Miocene. And so these fractures were much earlier formed when the chalk was probably not at its final stage in formation. So they're relatively early formed fractures, and we'll go through and illustrate how some of these fractures have formed as we go along. So the sort of feedback I've had from you, from workshops, and some of the typical questions have been, why the only thing we really need with the chalk is a fracture log? And I was told this quite severely once on one training course, logging teams to log the chalk. And you can imagine I did disagree a little bit. And hopefully tonight I'll show you that, yes, indeed, a fracture log is incredibly important, but also, if you're going to build ground models in the chalk, you need to know other things as well. The biggest issue seems to come up pretty well every time on every project. Can we really expect SI contractors to identify and log marker beds? And I'd like to go through this a bit, and perhaps by the end of the talk, you can tell me whether you believe, yes, you all can log the marker beds well. I often get asked, what are Marl seams? What are flint bands? And how important are they to engineering? Well, we'll try and go through some of those things as well. And I delight in getting questions, because I've been working on the chalk, 50 years now. And so the trouble is, I get so used to seeing things in the core and in the field, I forget that others don't realize what they're looking at sometimes. And so it's very useful when I'm out with teams and they say, how do you know that's a sponge bed? Or how do you know that's a nodular bed or a hard ground? And those are very useful questions. It forces me to think and to explain things better. And then I'm always asked, how do some of the fractures form? Well, we'll have a look and see if we can explain at least some of them. And we'll start with examples of fractures in core and in the field. And we'll particularly look at, in the beginning anyway, weathering, overprinting, other types of fracture. We'll talk about strata-bound fractures, which are very important to the chalk and its engineering. Primary fractures and bedding slip, we'll have a look at some elements of that. Growth faults, which are surprisingly common in the chalk, but are not really picked out very well. Evidence for strike slip. I'm often asked, is there evidence for strike slip faulting in the chalk? And hopefully by the time I finish this talk, and you will have been convinced, yes, there is evidence for strike slip. And then the other thing I'm often asked, particularly when in relation to things like tunnels, is how frequently can we expect faults? And we'll try and answer those questions. So we'll start, first of all, looking at the near ground surface and the weathering of the chalk. And here we have two different fracture patterns, one from a trial pit. This happens to be on the A27 Brighton bypass during construction, but this trial pit shows a typical ground profile from near the top surface, near the soil horizon at the top, coming down through the chalk, and you can see you've got horizontal fractures closely spaced, and they're open. And towards the top, you might notice, those of you who've got good eyesight, unlike me, if you look at the date, it's January 1991, and there's ice around every block. And what has interested me over the years is every time we've done a trial pit in the winter, and it's frozen ground at least down to 2 meters, we get ice round blocks. So the moisture must be coming in and out of the chalk on a regular basis, which must be doing something to its properties. In this particular picture here, we're looking at similar frequency of fractures and also open fractures, and it's structured chalk. But in this case, the vertical fractures are more closely spaced than the horizontal ones. And a question often arises, should we give 2 different grades to this? Yes, the fractures are all open, so it would be a Syria grade C. And those of you not familiar with Syria grades, and the trouble is, if I'd had you in front of me in the audience, you could all put your hand up and say whether you were familiar with it or not. But just to say to you that those who are not familiar with the Syria grades, they're broken down into 2 broad groups. One where we're dealing with what we call destructured chalk, if you like, in an engineering sense. You can still pick out layering, but from an engineering point of view, the rock is destructured and has a matrix of broken down material between blocks. So you've got destructured chalk, and then you've got structured chalk. And the structured chalk is further broken down based on aperture of the fractures. If the fractures are open by more than 3 millimeters, it's a grade C. If they're less than 3 millimeters, they're probably a B, and then you go down, if they're closed, they'd be an A. So that's the very simple classification that we use for the Syria system. And I noticed that the Syria is about to be, well, at least they're considering rewriting Syria. I hope they don't get rid of that classification, because it's a relatively simple one, which we've trialed now for, since 1989. So it's quite a few years that we've been using it and trialing it and getting it to work with all the different teams. And just to show you what a destructured chalk looks like, a grade D. So you've got a grade D compared to 2 grade Cs. These are structured chalks. This is destructured with blocks separated by matrix in various ways. So I'm not going to go into that classification any further than that. And just as a reminder to those who know it well, but also for those who've never seen it before, that's the simple classification that we use. And of course, when it comes to weathering and the stuff, we have all sorts of issues. Here we have a dry valley. It's given a brilliant name. I don't know who named it, Scratchy Bottom, this hard ground, this dry valley. But you can see the nearly vertical bedding. So we're in the Dorset Purbeck Fold belt, and the weathering has resulted in soil creep as well. So the beds are all overturned in the other direction, down slope. But you can see how deep below the ground surface the chalk is destructured. It's lost its true bedding structure, and you have a problem in trying to decide where it becomes a structured chalk. But you can still pick out all the layering going all the way through, and you can trace the layering moved down slope by the creep. Now, when you get more competent chalk like this, you tend to find in the cliffs and quarries and in most engineering projects that the competent chalk has a particular style of fracturing depending which formation you're in. And here we have 2 chalk formations, and this one down here is the Hollywell nodular chalk formation, and you can see these beautiful inclined conjugate fractures. And going across is the layering in the chalk. And these layers, these grey-green layers, are marl seams. We'll come back to those at a later date. But you've got beautiful inclined conjugate fractures. In this case, in the top photograph, we've also got inclined conjugate fractures because we're in another formation which is full of marl seams. This is the New Haven chalk, and this is New Haven cliffs. And the inclined conjugate fractures die upwards into the overlying formation, as the overlying formation doesn't have marl seams in it. And these tend to become vertical joints and fractures in the overlying culver chalk formation. So each formation does have its own characteristic fracture style. So if you like, they're strata-bound fractures. And this produces very typical cliff profiles and cliff geomorphology. So here in the New Haven chalk, you can see the influence of these steeply inclined conjugate fractures. And here again, it's closer up. But compare that to the Seven Sisters in the Seaford chalk formation, which is a much purer white chalk and doesn't have the same number of marl seams in it. And you can see you've got beautiful, clean vertical fractures and giving a cliff profile like this, which is very different to this cliff profile. So your geomorphology of your coastline is being influenced by the fractures within each formation. And this is very consistent. When I first showed these to the engineering group many, many years ago, I was told that this is all due to stress relief and nothing to do with the internal natural fracturing within the rock. Well, I'll come back to that again in a minute, but I'd like to first show you the influence of these fractures on different aspects of slope stability. So these vertical fractures in the Seven Sisters Seaford chalk formation, you can see the cracks opening along the top of the cliff here, and you're tending to get almost like big slab failures in the cliffs, all the way along the cliffs. And these can be relatively thin slabs, but taking out up to about 5 to 7 meters sometimes of cliff at the top. So we have to be pretty careful when we're getting close to the top of the edge of these cliffs. There are a number of issues with this, which are very interesting to the mechanics of cliff failure, but I'm not going to go into that tonight in any detail. You can look that up in this special publication that we produced some years ago in 2004 on chalk slope instability, chalk cliff instability. Now compare that previous type of failure with this sort of cliff failure, which is in the New Haven chalk. The first one was in the Seaford chalk with the vertical fractures. Here we have the New Haven chalk with these wonderful steeply inclined fractures, and you're getting a very different kind of slope failure. The primary fractures are all beautifully stained in the back, so you can see where they are. You're getting material failure as well, but these are falling out. And the idea of building a sea wall originally here was to protect these cliffs on the assumption that we wouldn't get the types of failure we now see, because there would be no undercutting of the cliff by the sea. It's been protected. The cliffs have been protected. But that doesn't stop these cliff failures occurring. But the scale and type of failure is very much dependent on the style of fracturing within the rock mass. And the style of fracturing varies with each formation. And this is just another illustration of the same sort of thing, but it's happening not just in the New Haven chalk. Here, the top of the Seaford cliffs, we've got New Haven chalk coming in, and where you get the New Haven chalk coming in, you're getting these inclined conjugate fractures. Here we have at Peacehaven cliffs, again, the same inclined conjugate fractures, but here at Eastbourne, we're in the Holywell chalk, and this time with, again, steeply inclined conjugate fractures and major collapses occurring along that coastline. So the style of fracturing is very much controlling both the scale and style of failures, slope failures in the rock. And this is not just confined to southern Britain. Here we are on the Yorkshire coast in the Flamborough chalk formation, which has numerous thin marl seams in it. And again, you can see these wonderful inclined conjugate fractures. So the style of fracturing appears to be particularly controlled by the type of lithology. Where we have many marl seams, we tend to get inclined conjugate fractures. And where we don't have the marl seams, we tend to get a greater concentration of vertical joint sets. And just in case you think that's confined to just the cliffs, these are cores offshore for a wind farm. But we've got lots of thin little marl seams in this formation, and we've got inclined conjugate fractures all the way through the rock. So we're seeing in core the same things that we are seeing in the cliffs. So we can use the cliffs to help us model the chalks offshore as well. And it also means that when we're in the downland and we no quarries and no exposures, but we know which formation we're in, we've got an idea of what the fracturing is likely to be in those formations. So if you're doing groundwater modeling or tunneling or anything else, you've then got a chance of predicting the style of fracturing you're likely to find. And I said to you that here's a beautiful picture of the Seven Sisters Cliffs, and you can see these beautiful, clean vertical fractures. And when I was originally told, no, this is just pure stress fracturing, I happened to be logging core for London tunnels at the time, and I did drop a piece of core. It's the best way to see the fractures. So I did. It didn't really damage the core too much, but you can see these beautiful vertical joint sets, exactly the same that we see on the coast, but here we're deep under London. So we're seeing the same style of fracturing in the chalk, but here they're all closed, whereas of course up here they'd be open. So when we get big complex high cliffs like Beachy Head, made of several formations, we get the failures, all the different types of fractures interlinking to produce different styles of failure. We're getting these huge toppling failures up at the top here in these vertical joint sets. And then as we come down through the cliff into the inclined joint sets, we're getting different scales and styles of failure. And if you want to look at that in any more detail, again, that's in that book, the special publication number 20, Coastal Chalk in Instability 2004, when we carried out a big program of looking at the cliff stability with our French colleagues. And just in case you think that is all purely coastal geology, when it came to the tunnel portal areas for this, in this particular case, it's the A26 tunnel at Lewis. The slope stability here at the North Portal was again controlled by the top end of the New Pit chalk, which is full of marl seams, and you've got these steeply inclined fractures. And as soon as we opened up the face on this slope, it collapsed along those fractures. And these fractures tend to be highly polished. They tend to be clay mineralized, so much reduced friction on them and cohesion. So you've got they fail much more easily. On the south portal of the same tunnel, you're in a different formation, the Lewis chalk, with numerous flint bands. And despite having steeply inclined fractures in it, potential failures, the flints crossing the fractures were actually increasing the friction across there. And this has been there that we thought this might fail relatively soon after construction, hence building the wall for protection. But this is now, when was that? 1979, 1980. So it's a good 40 years, and that's not moved at all. So the flints across the fractures are increasing the friction in a big way, the cohesion on the fractures. So there's interaction between lithology and marl seams. And then if you look in the openings of the tunnels, for example, an example here, where you've got marl seams crossing near the crown, you're getting release surfaces along the fractures as well. So the marl seams are critical to engineering in all sorts of contexts, and therefore they need to be logged. It's not just about the fracture logging. So that's a little interlude on lithology, fractures, and slope instability. The implications of these strata-bound fractures are many. Let's just give you a few. Where you've got closely spaced vertical joint sets, and you're looking at doing seismic studies on fracturing the ground surface or whatever, you're getting greater attenuation of seismic and acoustic signal in the inclined fractures compared to the vertical fractures, because you've got more airspace between the vertical fractures. But when you're looking at rates of opening of fractures, BGS, as part of a study we were jointly involved with, used azimuth resistivity to actually measure the opening of the fracture. So coming along and doing a resistivity measurement on the orientation and openness of a fracture every few months over a period of 3 to 4 years to see whether the fractures were opening. This was a good method to use when you're dealing with vertical fractures, but not such a good method when you're dealing with the inclined fractures. In the numerous closely spaced vertical fractures, you're getting focused groundwater flow. So the groundwater flow is much faster and goes almost straight through, with rainfall going down your fractures much more easily. You've also got easier excavation in earthworks, because where we've got the inclined fractures, the rock is much tighter and sometimes very difficult to break out. when you've got a lot of vertical fractures, the rock's much easier to break out. And the same goes for piling. It's much easier to drive into the vertical fracture sets than it is into the inclined sets. So in the inclined conjugate sets, we potentially get less attenuation of signal, for example, in seismic signal. Not so good for azimuth resistivity, and we get more focused groundwater flow. So you tend to have more primary fractures, and they tend to be clay. They tend to be clay mineralized along their fractures, which doesn't allow the interaction of water into the pores around the chalk quite so readily as it does in the clean fractures, vertical fracture sets. And so you're getting groundwater flow much more focused and going very rapidly down sometimes through this particular rock. It's tighter for earthworks and for piling conditions. And those of you who are interested in looking into a bit more into some of these aspects, there are a couple of PhDs, one by John Lamont Lack on the engineering classification of chalk with special reference to origins of fracturing dissolution. That's a useful one if you ever want to look at it. And James Lawrence's PhD on cliff instability in Northwest Europe is also a useful one if you're looking at wanting to understand a bit more about cliff stability. If you're interested in fractures in relation to groundwater, there's another PhD by Ian Molyneux on the characterization of the chalk, and that has some superb stuff in it, so you really ought to read it if you're interested in that. And Neil Hadlow is looking at the catchment ground models in southern England and northern France as well. So those combination of PhDs are all referenced, incidentally, in the 2018 Chalk Conference, Engineering in Chalk, which many of you will have read and presumably got. So these works will be referenced in there if you want to go back and look at those. Issues related to fracture logging. A question that always comes up is over what core lengths, depths should fracture frequencies be recorded, particularly in rock like the chalk when you've got no clear strata changes or boundaries. And this is the case when you're logging through much of the chalk. Should fracture frequencies and spacing match the Syria grade classification suffix? Because against every grade A, B, C in the Syria grades, there's a suffix indicating the fracture frequency from 1 to 6. And so it's actually important, I think, that any fracture logging that's done, the frequency of spacings ought to match up with the Syria grades, which they don't often do. And how to get the message over to designers about the nature of chalk fractures. And that comes back to the way we log and what we actually do with our core. I don't know how many of you have been faced with logging core like this. Heavily broken up, frequently happens to me. I get called in sometimes towards the end of a project and after the core has all been broken up and looked at, and people say, can you please tell us what grade that is? And I look in despair initially, but actually there's a lot there that you can deal with. You might think that's impossible. And most of the core has been broken up by drilling and, of course, by those doing the logging. And wherever you've got flints, it tends to break up. But in some places, you can actually see there's dirt on the fractures. So if you've got a filled fracture, that would be a grade C. In other places, you can see you've got fractures, but they're not really opened at all. And that might be actually closed fractures, despite being very weathered-looking chalk. So you might have a mixture there of a B and a C, or even an A. So what grade would you give it? Well, I think the way in which we generally approach this is to give it the worst grade. So where you've got open fractures and they're filled, where you've got filled fractures, they will be open, and that would be a C. So you'd probably give that whole core run and this core run a C. But, it's to some extent, you've really got to work hard to dig in there and look at the fractures that have been broken up. And here, before logging has been completed, sometimes the core comes back and the driller has managed to break it up, and the core breaks up along fractures very regularly. And all these areas of broken core are actually due to drilling. This here at depth, at the greatest depth, that is almost impossible to give a fracture log to. I wouldn't even attempt it. And I think you just have to say that over that interval, it's not possible to provide a fracture log. But interestingly, there's no indication of any dirt in there, no indication of staining on the fractures. And therefore, the rock is probably, before it was broken up by drilling, probably drilling into a lot of fractures, it was probably a structured chalk. And sometimes for the designers, they need to know, they need over those intervals of rock, they need to know what sort of grade they're dealing with. Now, sometimes you can use camera logs to put down the boreholes and have a look and see whether what you think it is correct or not, but you may not have that always, and you've just got to deal with what you've got there. So I would tend to log in core runs, but I would also always agree a procedure with all the teams, both the consulting side of it, the client side of it, and the contracting side of it. You need to agree a procedure with all the teams that you're going to come up with an answer that they can all be happy with. And that's where you'll see at the end of the talk, I think workshops are so important. If you're finding you've got problems with core and core logging and the issues that are being raised, it's always useful to have a workshop, bring everybody together. Here we have an indication of core fragmentation quite deep down. You see, this is 90 to 93 meters depth, and you might expect the chalk to be nice and tight all the way through. But because of the fracturing, the drill bit has actually broken up the core all the way through. And you see the joints and fractures in here are stained, and they're quite heavily stained. But actually those joints, when you do get a decent bit of core, you can see that they were closed. So most of that would be closed grade A, but it would be logged probably by those who are certainly not inexperienced or don't have the confidence to do so, would log it probably as a grade C, open fractures all the way through. And that has a huge impact on design and depth of putting piles in some areas. So you need to be, this is again where it's a good case of needing to have a workshop to have an agreement on what you think those grades are. And in the overlying new pit chalk formation, a considerable depth still, you can see you've got inclined fractures which are causing the core to break up. So breakup of the core by drilling is very common, and then the loggers are left with the issue of trying to interpret that core to see whether or not it really is a C, a B, or an A. Fracturing and tectonics. Bedding slip structures, we'll have a look at that. Fractures in folded chalk, well, we saw a bit of that earlier. Fractures and shear zones, faults and extent of damage zones. Now, damage zones are sorts of things that the hydrocarbon companies and groundwater people need to know. What are the scale and size of damage zones along faults? And strike slip structures. So let's have a look at, again, folded chalk. This is on the Isle of Wight this time. Here we've got a unit of chalk with numerous Marl seams in it, and we've got inclined conjugate fractures crossing the rock mass. Very common. And so each one of these little strips that you can see here is a thin little Marl seam in the rock. And this compares with the same unit of chalk here, nearly horizontally bedded, but in the cliffs at at Peacehaven. And again, you've got the Marl seams, but you've got inclined conjugate fractures crossing the rock. And that's very typical in these marly chalks. But we also have many of the shear planes within the rock mass, both along the fractures, the inclined fractures, and along subhorizontal features, have been replaced, in this case, by flint, sheet flint. These are not the nodular flints that's common that you would normally see in the layers of the chalk. These are actually formed along fractures. So these are related to the fracture formation within the chalk and fluids being pushed up those fractures, and those fluids precipitating out silica along the fracture zones. And you can see all sorts of sense of movement. We've got a Marl seam here. We've got a fracture coming up that's possibly been offset from here to here. And we've got other fractures here replaced by sheet flint, these dark layers of sheet flint, but multiple fractures. So we've got horizontal movements and we've got inclined conjugate shears developed. And along these, we've got the sheet flints are formed along the fractures as well, and frequently offset along each Marl seam, which I'll show you more clearly in a second. And then we get these types of structure within the chalk as well. Here, this must have been very poorly consolidated, high porosity chalks, still a lot of fluid in them, and the movement, the shear movement along the surface, along a bedding surface, has caused the fluid to actually be to develop a fracture system, and a network of shears and a network of veins that are almost like sedimentary dikes. It's pushing all the fluid out into the fractures as they form. Now on this picture here, these Marl seams here, you can see each Marl seam has offset the fracture. So there's a lot of movement taking place in the chalk, and that movement is being enhanced by the fact that you've got these weaker zones, these Marl seams, where the stresses are focusing within the rock mass, and that's where you're getting your main movement taking place. And then in this particular case, you're getting a whole series of fractures developing as the rock moves. You're getting fractures developing, and here you can see the sheet flint on a fracture has been offset by movement along even a very tiny, thin grey Marl seam. So when I'm asking the loggers and the SI contractors to pick up all the Marl seams, I'm not asking them to do it just for fun. These little thin seams actually have a huge impact on the mechanical properties of the rock mass. And then we get chalks like this, which again, with lots of Marl seams in them, and inclined conjugate fractures, but they also have these lovely polished striated shears, which many of you would have seen. But the other thing they have is zones of fracturing. So you're getting intense fracturing, and then counting the number of fractures in a zone becomes quite critical. And the way I've decided to start doing some of the logging for this, and again, you can see you've got beautiful striated surfaces. This is on a subhorizontal fracture. This is on an inclined fracture. So you've got inclined fractures and you've got subhorizontal fractures, all showing sensors of movement on them. And the way I've tried to accommodate this in a core log is to show where we've got intervals with multiple fractures developed as shear zones. And it isn't in every part of the chalk that you get this, but there are some areas of the chalk downland where you're getting these intense fracture zones, and those intense fracture zones will be enhanced permeability horizons. There will be enhanced instability horizons in slopes and tunnels. So actually picking these out over and above your normal grades and your normal fracture log, I think is useful. And of course, sometimes these days we get downhole camera logs, which are brilliant, and they enhance and help us identify these fractures and recognize that they are real, and that you've got groundwater flow along those fracture systems as well. Now, one question I've regularly asked again is there evidence for strike slip movement in the chalk? Well, here in the New Haven Cliffs, a great place to go and study fracturing in the chalk down at New Haven. And here you can see these beautiful near horizontally slick and sided striated surfaces on these fractures in the chalk. And these are fault movements with many of them all the way through this cliff showing strike slip movement. So they are common. And when you start to look at areas of cliffs like this at Beachy Head, here's a big fault zone at Beachy Head. And when you look at each one of these a bit more closely, each one has subhorizontal slick and siding on them. So you've got a lot of strike slip movement on many of the faults, and you can see how frequent the faults are. Incidentally, we wouldn't be able to pick these faults out unless we had a marker bed. And I know you can't see this very well, but that is the Seven Sisters flint band. And it's when you pick it out, you can actually then use it as a guide to show how frequent the faulting is. And what about growth faults? You can see this fault up here has no displacement between those two flint bands. And the displacement, if you look down, increases as you go down from a few centimeters up here to half a meter here and progressively down. And there's a whole series of growth faults in this rock mass in the New Haven Cliffs as well. So growth faults actually are quite common, but in particular formations. And just in case you think that that's of not much importance, but it doesn't, it is confined to those cliffs and so on. This is an offshore and rather exaggerated vertical scale. Sorry for that, but nevertheless, this is on a fold. And if you look at the formations, you can see how the fold has controlled the thickness and development of this particular unit of chalk. And also, there is a difference in displacement on this fault here compared to here. So these are, and it's reversed. So what you're getting is an inversion fault developing, and it's growing in the opposite sense as you go higher up into the chalk. And that's a very common feature in the chalk, because the chalk period was when the major period of inversion was getting going, and then reached its climax in the youngest chalks, which we're only just beginning to realize how important that has been to our studies. Now, what about these marl seams? Marl seams have been controversial for a long time. There are still papers out there which suggest that all this clay in the chalk and these wispy clays are produced by dissolving away the carbonate and leaving behind the clay minerals. I've always wondered why people have written that, because when you look closely at these clays, you can actually see they are peppered with burrows. So these clays are primary on the sea floor, and then various organisms have left behind their traces within the clay matrix. You've got some larger ones, these thalassinoides, which have become progressively squashed as you get towards the areas where the main clay zone is. So they're getting squashed from being more circular to more elliptical. And then these trails are also being squashed. And that gives you this horsetail type structure within the rock mass, which is actually nothing to do with complete dissolution of the chalk. It's just that you've already got a fabric which is focusing stresses down onto these marly weak layers, and you're getting shearing along these surfaces. And as a result of that shearing, you're getting squashing of the original features within the rock. Some marl seams have none of that. This is a thick marl, a typical marker bed marl within the chalk, and that is a volcanic origin. We know it's a volcanic origin because it's a very specific and special chemistry. So there are volcanogenic marls as well as marl seams like this. And the importance of knowing that these are primary features is that we know they're there when fracturing starts to occur, and it relates to all the early form fractures as well. You're getting squashing and movement along these clays, which is enhancing horizontal movements, which is changing the orientation of the stress field within the rock mass. And so you're getting inclined conjugate fractures developing. Applications of the marker beds and assessing ground risk. And I think identification of stratigraphically significant beds for engineering has enormously enhanced our onshore-offshore link geology that we've been doing, especially with the offshore wind farms. It was also very important to recognize these features in terms of groundwater and karst development and links to geophysical logs. We'll come back to all of that. So here we have some wonderful core from offshore. And in this core box, you can see you've got this enormous thick flint. And this is a continuous solid piece of flint. And that solid piece of flint, which is more than it's up to 300 mils thick, is continuous over vast kilometers, hundreds of kilometers. So it's not just a single isolated nodule. These are what we call tabular flints. And here we also have a key marker marl seam, and we have other thinner tabular flints. And this succession of marl seams and flints is characteristic of a particular unit of chalk. This happens to be in Yorkshire, Northern England. And here's one of these flints that is not nodular, but is a thick tabular flint, and is continuous over many, many thousands of kilometers. So if you're drilling into it, you're going to hit it pretty well everywhere. If you're putting a boring machine in for cables or whatever, that's going to be over a very long distance. You want to avoid those if possible. And we know where they are because we've done enough stratigraphy in the chalk now, studied the chalk sufficiently well, and we've got good logs for all the coastal sections and good logs for the boreholes. We should be able to identify pretty well where we are in the succession. So that big, thick tabular flint I was showing you earlier, the Ludborough flint, and there's the North Ormsby Marl. This is on cliffs near Flamborough Head in Yorkshire. And then we can compare that directly with North Lincolnshire, a geophysical micro-resistivity borehole log with spikes in this direction representing marl seams. And there's the North Ormsby Marl, and there's the North Ormsby Marl here. Then we've got the Ludborough flint, and we've got the Ludborough flint here, and the spikes in blue in this direction. Those spikes in blue, the thicknesses of those spikes is a good indication of the size of the flint as well. So you're getting a very good indication from geophysics of the size of the flint, and the size of the spike in this direction is giving you an idea of the thickness of the clay seam, the marl seam within the chalk. So you can use geophysical logs to actually begin to characterize the lithology very accurately in some areas, not everywhere, but certainly in areas like this. And that's a micro-resistivity log from South Killingham. It's in the book that Vicky was selling for me earlier, the beginning. Now, some flints like this are giant and they're solid. And if you were sitting in front of me, I'd ask you, in terms of MPa, what strength you thought normal chalk would be. And of course, you're not there to answer these questions, so I shall just say the chalk, the ordinary soft white chalk is about 4 to 8 MPa, and the harder chalks that we've been looking at maybe up to 20 MPa. And when you then start looking at the strength of flints, flints start at about 100 MPa and characteristically about 250 MPa. But when you get these giant paramudra flints, you're talking about things which are, when we've tried to crush them in the big machines, they go up to over 1,000 MPa. So within the chalk, you've got two completely different materials and totally different engineering characteristics. You've got the flints, which can be extremely strong, and you've got the very weak chalks. But these giant flints, we know, only occur in certain intervals. So if we know our stratigraphy, and if we've got the marker beds correctly identified from core, we can build a ground model to begin to show where the risks are going to be for things like piling or drilling or directional boring. So we have intervals, for example, like this, where we've got the tabular flints you want to try and avoid. You've got intervals like this where you're going to potentially hit giant flints like these, and in between you've got better conditions for most of these engineering operations. So knowing your marker beds and building the ground model like this becomes quite important for a number of engineering operations. And it's not just up there in the Yorkshire coast. Here we did the same thing under London for most of the tunnels in London, and here it's gratifying to see this because these are my original borehole logs for some of these boreholes, and I picked up the big flints, and then when the camera logs were put down, you can start to pick up the big flints again, and then the electrical resistivity logs also started to show the same flint band. So you've got three sources of information confirming the big flints that you're going to be going through with the tunneling machines. And one of the things that the TBM designers wanted to know and the engineers wanted to know was the percentage flint in any face, the frequency of flint, the size and strength of each flint band. Well, to do that, you've got to know your stratigraphy of the flints, and you've got to have recorded them correctly in your core log. So it's important that when we're core logging, that we don't just dismiss things and say, oh, it's just a fragmented, broken up flint, therefore it's flint gravel, which is a complete misconception. These are layers. These flint bands are layers, and they need to be identified as beds and layers on the logs. And of course, some of them can be very seriously large, even for large TBMs, so they wear down the tines relatively rapidly, which has its own issues. Now, there are occasions when we want to be able to confirm these types of correlation using other aspects of geology, like the biostratigraphy using macro and microfossils and nanofossils. And there are places where in the chalk, we don't get lovely marker beds like this. We get long lengths of core without anything. And in those cases, we turn to the people who are specialists in the nano and microfossil, and they help us sort that out. But the other thing we've done also is to sample every single one of these boreholes through London for micro and nano, so that we build up a picture of the stratigraphy of these for the biostratigraphy in detail, so we can use that elsewhere. And the macrofossils can be incredibly useful. They help confirm the correlations we're making. If we're going to build our ground models, we actually need the macrofossils as well. And these are different types of inoceramid shell that have been found in core. I've never seen such a fine example as this Volviceramus as we pulled out of core. This happens to be on the A303 Stonehenge boreholes. And these here are Dover tunnels and places of a different type of inoceramid. This one has a wonderful name like Cladoceramus undulatum, and this one is Volviceramus. They're completely different, but one occurs above the other. So you know where you are in the succession. As soon as you find these, you're confirming where you are in the chalk succession. Geophysics has also been used to identify rather special types of chalk. The phosphatic chalks have a very high gamma count. And so these are gamma logs, which are picking out the concentration of phosphates in the chalks at various places. And when you look at the phosphatic chalks, you can see they're very different to the pure white chalk. Here's the pure white. This is a core going from pure white chalk into the phosphatic chalks. And you can see the change in color instantly. And this is rather like a sand. It can break down very easily like a sand in your hand. So a very different material from an engineering standpoint. We also use the geophysics to help us work out what's going on laterally in the chalk. In areas of the Chiltern Hills, for example, where we have the chalk rock, you get a highly condensed succession of chalk with hard grounds. As you come into the North and South Downs, however, further south, that little unit there expands up into this unit here with lots of different marker beds. So one of the things we've learned is, yes, we can use marker beds to build wonderful ground models, but those ground models may only be relevant to that particular area that you're working in, for example, the Chilterns. When you come down to the North and South Downs, you've got a different type of succession and a different marker beds to pick up. And just to give you an idea what that chalk rock means, if you've not seen this before, this is a surface of what we call a hard ground. It's green, it's mineralized with glauconite, it's mineralized with calcite, it's mineralized with iron, and it's also mineralized a bit of phosphate. And it's got a bored surface on the top. And we call them hard grounds because the chalk seafloor has changed from being a soft, soupy sediment when it was first formed, with animals being able to just easily burrow into it, to something that's become so hard it's cemented on the seafloor that you can no longer burrow into it easily. You have rock borers. So the ecology has changed, and that's why it's called a hard ground. And it's a hard ground with respect to the ecological change that's taken place. But these surfaces are wonderful surfaces for following through the chalk because they actually tend to form on channels. And I'll show you a bit of that in a minute. Here's that same hard ground, but this time in core. And I don't know whether you can see the fossils inside here, but these were originally what we call aragonitic fossils, things like snails and ammonites. And the calcite, the aragonite has dissolved away and the carbonate has cemented this into a very hard rock band. So these are very high density layers. And actually, where these are present, particularly if you're piling into them or offshore, particularly in the offshore piling industry, these are surfaces that require pre-boring rather than being able to drive your pile straight into it. And they also form on surfaces like this one here. This is a hard ground forming, and you can see it in the cliffs, and it's forming a channel, a slope. And where you've got karst features developed, these dissolution pipes are coming down from the top of the cliff onto that surface. So this surface is controlling the depth to which karst has developed within this ground. So here they're coming down to relatively shallow depth. Here they're coming down to depths greater than 90 meters. So you've got a huge difference in the depth to which your dissolution features have gone, and it's been controlled by that hard ground surface. And here is that hard ground surface. When you look at it, there's so much water come down through onto that surface, it's dissolved out the borophyls, the softer layers within the hard ground. And just in case you think that's only present again on coastal areas, here in the Chiltern Hills, this is the chalk rock with exactly the same things happening to it. So it's a surface along which groundwater has concentrated within the rock mass at some stage in the past, and it's dissolved out in the same pattern as you see here on the coast. It's dissolved out the burrow systems. So water has concentrated on these surfaces and created a karst feature. And some layers like this flint band here, we've mentioned the Seven Sisters flint band before, is such a continuous layer that groundwater again has come down through the rock mass, down onto that surface, and there's an underground stream has formed along it, creating these cave systems. Further away, you can see the cavities are still filled with sediment that's been washed along. Here, the sediment's all been washed out. And here we have a marl seam. This is in a big quarry where groundwater has come down onto this surface, and you can see where the seepage is coming out along it. So in terms of groundwater and groundwater modeling, we know now how important things like marl seams and flint bands and hard grounds can be to altering the groundwater flow from just being purely vertical down to a water table to actually horizontal flow. We know this much more now because of camera logging so many boreholes in both the North and South Downs. And we can see the groundwater flow coming out along these features. And here is the chalk rock top surface, is 86 meters down, and you can see the cavities that have formed along it. And here is on the coast, you've got marl seams, and you've got masses of tufa, beautiful stuff, formed along where groundwater is coming out along marl seams. And here you've got hard grounds with again, controlling groundwater flow within the chalk. So there are features within the chalk, such as marl seams, hard grounds, flint bands, which need to be logged because they also affect the way in which groundwater flows. And we can see that past karst has developed also on these sheet flints. Here are two sheet flints, and above the sheet flints, you're getting this wonderful mealy textured, dissolved out tubular karst. This happens to be in Dorset. This one is locally in the Sussex Downs, and there's another sheet flint here. And we had huge meters. We actually had a section of nearly 20 meters of chalk, which had dissolution in it like this. And in terms of the road cutting, I think it was up to 30% the volume of chalk had gone from that road cutting that they were expecting to use in the earthworks operations. So the impact of the karst, although it's not massive karst like the Carboniferous limestone with huge underground rivers and streams in it, there's still plenty of karst to consider as an engineering risk within the chalk. So role of marl seams in deformation of the chalk and engineering. We've seen bedding slip along marl seams, a common feature. We actually get disruption leading to extensive slides. We get rupture of chalk blocks in glacier tectonics. If you want to go along the Norfolk coast and look at the big blocks that are incorporated in some of the tills along there, they've been ruptured, they've been broken away from their original bedding along marl seams. We know the marl seams are controlling groundwater flow, slope instability, stress distribution in tunnels. Marl's even thin interwoven seams are really critical to understanding mechanical behavior, and they need to be logged. So what I tend to do with training, and I do find it's really good if you can get out, we have two approaches. I run a course before start of drilling and logging, follow up with logging a standard core for everybody then to be able to use as a reference for all the rest of the core, and reinforce that with subsequent visits. Or I go up to a site where they've already got the teams already working and logging, and log the first core and then run a workshop on that site and on that core. This provides a standard for everybody else to work with. And I think there is a need to provide more annotated logs, identifying fractures, as I've indicated earlier. And the one thing I do think we don't do very well in the industry, we provide wonderful data, wonderful core photographs and things like that, but none of the core photographs are annotated, picking out features. Seems to me the photographs are almost put in there as because they're required rather than because they're going to be used well to define things. So summary, we need more than a fracture log. And the reasons to log the chalk in detail include these sorts of things: borehole correlation, boreholes linking to field sections. And a very simple thing, if you don't know where you are in the chalk, you can't go out and sample the quarries and cliffs to check to see what the properties of those particular units of chalk are. Recognizing fracture styles, or beginning to predict perhaps what the fracture styles are likely to be. Interpreting geophysical logs and seismic sections, vital, absolutely vital. And interpreting geotechnical results, test results. If you've got a framework with the properly modeled chalk sections showing where you are in the section, your test results can be put into a framework and used to predict the ground much better. And as you've seen, some of the features in the chalk are also determining the degree and depth of weathering that's taking place in the past. Then there are other things like horses for courses. When do we use micro and nanopaleontology and biostratigraphy and geophysics for that matter? And so fracture logs or Syria grades are not adequate on their own. We need a good description of the rock as well. And yeah, I suppose one thing, all staff can be trained to log marker beds. I was told they couldn't be. And I was stunned when I went up to a project. It was one of the, I think it was partly Crossrail or HS2 at the Euston Station. And the guys doing the logging there, and I looked at their logs and they were brilliant logs. And I said to one of the guys, how do you where did you get all your training to do this logging? You've done a fantastic job. He said, no, I just picked up your book and read it. I thought, wow, that means I don't need to be everywhere training them. The book works. So we started with tongue-in-cheek, all we need is a fracture log, because that's actually what I was told by one line manager on a project. But that's just not the case. And we do need to go beyond standard practice in the way we record the information, I think. And the value of recognizing the unusual, where your fracturing is unusual, where your lithologies are unusual. There's an enormous value to that because it's telling you a lot about the potential geology. How to collect and communicate the information needed over the lifetime of a project. The thing is, we tend to only be at the beginning of the project, you're drilling on your cores and dealing with it, but over the lifetime of a project, you frequently need more information than you're collecting at the beginning. When you've got things go wrong or you need more information. And some organizations I've worked with run workshops almost the end of every week on all the logging and engineering they've been doing. And they learn the lessons from that, which is very good. And I don't think we do enough in the way of workshops pulling information together. I know it's very difficult with big projects because of the timescales involved, and the people who originally did the drilling and logging have gone, and you've got new teams in. But it would be great to have more and better workshops sometimes, because that solves a lot of problems. Okay, Vicky, and all of you, well, you've done very well if you stayed awake and listened to me through all of that. Thank you for doing that. And thank you for the Thames Valley group for asking me along to give the talk. And happy Christmas to you all.
Thank you very much, Rory. That was fascinating, and I just love the slides and all the really detailed information just packed in there. Is incredible, and it's great to know that that knowledge is actually being circulated and used on a day-to-day basis by lots of people.
Yeah.
We've got already questions in the chat, which is brilliant. Can you see the chat, or do you want me just to read them out for you?
Shall I stop sharing this? Stop sharing the screen?
Oh, it's absolutely that's absolutely fine. As it is, if you can't see the chat, I can read what we've got there so far. So
Okay.
I think we've got something from Jeremy Daines, who is talking about it's quite interesting to see the large amount of uncertainty in evaluating cored chalk, and from his oil and gas background, typically calls the clastics of mineral uncertainty. Carbonates have more uncertainties with chalk. It would seem that if you have a heavily broken core with large uncertainty, then high resolution borehole images are needed to achieve a confident evaluation. I'm guessing clients don't understand the value of acquiring such images, expecting us to be definitive with a bunch of broken up core pieces.
Yes.
Discuss.
Thank you. I fully sympathize with that question. Yeah. I've seen it so often. And this is why I think teamwork is so important, getting the clients and the consultants and the contractors and everybody in early on to agree what it is you want from the core, and also coming to see the core and realizing that it isn't an easy task to get the sorts of information that they were hoping to get. And then needing other means, other ways of determining what that ground might be like. I mean, the consultants and the clients are usually in a better position than the contractor, because they can put a lot of information together, like the downhole camera logs and downhole geophysics. And if you're doing groundwater, they can see where the groundwater is going out of the boreholes and things, and where the fracturing might have be increased as a result. So they've got a lot more information to play with, but it's still, I believe, we don't do enough of that basic teamwork right at the beginning, getting everybody together.
And we've got a few more coming through. Louise Knight has asked, have you done a lot of work on the Isle of Wight? And do you have an inside knowledge about the recent Bonchurch landslip?
Years ago, lots of work on the Isle of Wight, but I'm not an expert on the Isle of Wight, and it's got its own wonderful expert geotechnical team, or used to have. I don't know where they've all gone now. The only bits that I know are the bits where the chalk at the western end of the Isle of Wight and the military road and the military road cuttings have caused an issue. The other types of landslip are very much related to other parts of the Cretaceous succession, so I would leave it to others to answer that one.
But other people to come up with answers later then. That's we've got another one from Julian Mould, who says, why do you get steep angle conjugate faults in chalk with marl layers and vertical faults in chalk without marl seams?
Yes, I wish I was sitting in front of you just to give you a feeling of what might be going on. I mean, normally one thinks of the main stress fields operating in the chalk, if it in any rock, as being a vertical stress down through the rock mass. But if you've got things like clay seams and marl seams, and many of them, what you're doing is switching those stresses down onto the horizontal planes, and so you're actually changing the orientation of your stress axes. And as a result of switching the stress axes, you're getting inclined conjugate fractures developing as a result of almost stretching of the rock along the Marl seams. So the Marl seams are creating these mechanical discontinuities, allowing the rock to move. Whereas if you've got a homogeneous homogeneous rock mass, and you're just stressing it vertically, you're more likely to get a standard vertical fracturing because your stress orientations are different. I hope that helps. Does that I get no response, of course. I can't see whether what I'm saying is making any sense to anybody.
It was a very clear explanation where I think I got it, which is good.
Good.
I think we've got one from Charlie Payton. He says, how much can you use surface staining to assess how open or closed a fracture is in core?
How certain can you be?
Yes.
Very uncertain sometimes. There's usually an indication where you've got drilling fractures, and there's usually an indication where the fracture is natural. And the natural fractures will have a staining on them, which will be very different to the drilling fractures. And drilling fractures do tend to have a conchoidal surface to them, like a shell. It's been broken, a conchoidal type surface. It isn't always a guarantee by any means that's the case. But aperture, because aperture is so important to the Shear classification, it's a thing that's driven a lot of minds over the last 20 years, 20, 30 years, trying to get it right. And all you can do in many cases is say that there's no staining on the fractures. The fractures look as though they were probably closed before the drill bit went in. But as you saw from some of the core I was showing you from 90 meters down, for example, in the Holywell chalk, the drill bit has broken it all up, but you can still see the natural fractures and natural fracture staining on there. And the surface and the two sides to the fracture fit together perfectly. And so I suspect the drill bit has actually caused it to break up. But that can happen at all depths. So it's and the fractures can be closed at all depths or open at all depths. So it's not 100% guarantee in terms of applying a grade. And that's where you do your description first, always, and then you do your classification second. So your description would describe the nature of the fracture frequency or whatever, and the staining on the fractures and whether the fractures are filled or not. And from that information, you would then provide a Shear grade. And I'm not sure that is always done correctly. It's very important that description is there as well as classification. I've been in court sufficiently often having to hand my notebooks in and things like that and cross-examined by QCs who say, what's the evidence for these fractures being open? Or what's the evidence for the strength that you've applied to the chalk here and so on? And if you haven't described your method in your log, and you haven't said, well, if I'm testing the strength, this is how I've done it, then you can be very open to a lot of criticism. So both in terms of the strength or the density of the chalk and in terms of describing the fracturing, it's very important that the description is there to go alongside the classification. Again, I don't know whether that's helped.
I think that's very good. I think we've got a couple more things on the chat, and I think we'll close that there on terms of the chats. We've got another question from Jeremy. He says, can you remind me on the genesis of tabular flints, how they're formed? I'm currently consulting on an onshore geothermal well in Denmark, which has just struggled through 1,800 meters of chalk. Tabular flints were probably one element of that struggle.
Yes, I again sympathize entirely. The formation of flints is a fascinating one. And as you're working in Denmark on a project, the Danes and the Russians have one idea about how flints form, and we over here have another. I think on the whole, when you look at flints, they tend to have a shape to them which relates to the original sediment. So they're replacing the sediment. So the flints, and within the flints, you can find all the original textures of the original sediment, as well as the fossils, all silicified. So that suggests that flint is post-sedimentary, is forming within the sediment, and the model that people have developed over the years for that is a biochemical model driven by bacterial decay within the sediment. Now, I'm sure you're all gardeners of some sorts, or fishermen, and you've had a bucket full of leaves over the winter, and you then come to tip that bucket out in the spring, and it stinks of bad eggs. Well, that's the H2S developing as the result of bacterial decay. And of course, the seabed is no different. You're burying huge amounts of organic matter on the seabed, including all the chalk, which is made of coccoliths, which are all coated in an organic, they have an organic outer coating on them and inner coating with them as well. And that all decays over time within the sediment. So you're generating an awful lot of H2S below the sediment water interface, down within the chalk. And that H2S will migrate up towards the seabed, and it'll meet oxygen being brought down by animals burrowing down into the sediment. And where you get that mixing zone, you're getting a change in the pH, and that's the redox boundary, and you can dissolve carbonate and precipitate silica, because carbonate and silica are at the opposite ends of the precipitation dissolution field. So you've got to get silica to form in layers or to form as flints, whatever, whether they're tabular flints or whether they're nodular flints, you've got to change the chemistry in the sediment somehow. And that is driven biochemically. I've given you an incredibly simplified view of that, because there are quite a number of different theories, but that is the basic theory, that it's a biochemical driven change within the sediment. But you've got to somehow dissolve carbonate and replace that carbonate with silica. And that can happen as a layer, or it can happen as around burrow systems, giving you those wonderful shaped flints that you find, or it can happen later on when you're getting the fracturing of the chalk, or relatively early fracturing of the chalk, and those silica-rich fluids, because the process is going on all the time, silica-rich fluids are squeezed up the fractures and replace the fracture walls. If you actually look at those sheet flints forming on subhorizontal or inclined fractures, if you look at those sheet flints carefully, you'll see the original fracture as a thin white line in the middle of those sheet flints. And so the flints have actually replaced the walls of the fracture, whether they're subhorizontal or whether they are inclined. That's a slightly different process to the original nodular and tabular flints, which are forming as a replacement of the sediment. But when you've started to develop that process, you've got excess silica fluids then available to be squeezed up fractures. Silica-rich fluids, which then meet the carbonate ions and precipitate out. Lot more complicated than that, but it's as far as I'm going to go.
It's fair enough. It's getting quite late in the evening.
I'll need a whiskey after this.
Yeah, I think you deserve one. We've got just a little aside. It's not so much of a question, but more of a comment from Edward Bromhead. He says, McDowell took myself and others to the buster cutting on the A3, where he told the contractor, who was having difficulty ripping the chalk, that he encountered the Melbourne Rock, which shouldn't have been a surprise, as it was on the geological map, a hard ground, as it was in the 1960s.
Exactly. Very good, Eddie. Yes. Yeah, well, you can lead them. You can lead a horse, can't you? But that is a question of getting the message over, and that's teamwork. Comes back to teamwork again, and really getting the message across to everyone involved in a project. What the geology is going to do to you. Sometimes it's not well communicated, and that's the problem. And another issue, of course, is how well the teams, everyone in the team can really understand the geology you're trying to explain to them.
Definitely an important thing to remember.
Mm.
Rory, thank you very much. I would like to say to everyone else, if you could sort of show your thanks by unmuting and maybe doing a bit of a clap, that'd be brilliant. Or just use the Zoom thing, that'd be great. But thank you very much, Rory. That was really good talk, and thank you very much for the Q&A session afterwards as well.
Thanks,
Well,
Rory.
Good. Well, thank you, Vicky, and thank you, the Thames Valley group. Brilliant.
There are some claps coming through, you can hear them.
Good. Okay. Well, have a good Christmas, everybody. And
yes, and just before everybody leaves, just a quick note to members that we are still working on the 2024 program. I can't believe how close that is now. So there will be some details coming out on that soon. If you do have ideas of things you'd like to hear about, or maybe you have something you'd like to present, feel free to get in touch on the TVRG secretary email that you got a lot of this details for this evening. And also we are on the lookout for new committee members for next year. So if you can think of anyone that's keen to be, say, a treasurer or do chair, or just on the committee in general, or a secretary, just let us know and we can tell you all about it. And there will probably be some more details coming out in the coming week. So thank you very much, Rory. Thank you very much, everyone, and have a happy Christmas and enjoy the whiskey afterwards.
Yes, indeed. Thank you very much, Vicky. Bye now. Bye, everybody.
Thank you. Bye.